I got all the way down to -4.
Greetings and welcome, friends. Make yourselves comfortable. Settle in for a nice little math video. It's been a while before we've talked about the equation of line. In fact, I don't know if I've ever talked to you guys about equations of lines. Not publicly on the internet, anyway. But let's flash back to those times. We'll make pretend like we were best friends a long time ago. We'll do a little recall here. Remember all those times we'd hang out and talk about equations of lines? Yeah, you know those equations like slope-intercept form. Right, slope-intercept form, you might remember that was y equals mx plus b, where, what was m back in that day? M was the slope, right, rise over run, and b was the y-intercept. Right, good times, good times. So you've seen equations of lines represented in that way. That's probably the way that you're most familiar with. Most familiar. There's also point slope form, which is actually, it might be in my mind the most useful, even though it's not as popular or famous as slope-intercept is. But that was y minus y1 equals m parentheses x minus x1. And the things valuable about that was, well, first of all, it had a slope there, so you could guess that the m is probably the slope. And the point, we have a particular point x1 comma y1. All right, so you've seen equations of lines perhaps written in that form as well. You might even recall standard form, which oddly enough is kind of the least standardized form between all of them. For some reason, textbooks and mathematicians can't agree on what it looks like. But sometimes it's capital AX plus capital BY equals C. Sometimes it's capital AX plus capital BY. I think if I write minus C equals 0, that might be the most helpful here. Question, comment?
Yeah. Do you mean to have a comma and then a space and then a comma and then a line?
Those are ones there.
That's a 1. Okay.
Yeah, that's a tiny little subscript. Good question, though. Yeah. And for standard form, well, actually, A, B, and C don't necessarily represent anything in and of themselves. Although sometimes standard form would be helpful in word problems, like if you earn like $3 for every X and $5 for every Y for a total profit of, right? Sometimes it's easy to write equations that model things within the real world using standard form. I mean, you can still figure stuff out with them, but that's that. So today we're going to talk about an entirely different way to represent the equation of a line, which is called normal form. Normal form. And just a question, do you guys know what a normal line would be? Maybe from your physics experience. A normal line is a line that is perpendicular to another line. Okay? Is a normal. All right? So maybe you've had physics problems where it's like, you're pulling a thing up a ramp, and it's being pulled by a chain perpendicular to the ramp by an individual, right? And like the person's like pulling it, there we go. And there's the concept of the normal force, where the normal force is perpendicular, right, to the ground. There's like the normal force, something like that. Does that sound vaguely familiar? Perhaps. No? Okay. I thought maybe you'd seen that before. Where, yeah, normal is perpendicular. And that's the same thing for us. So when I talk about normal form for the equation of a line, let me actually show you this sweet little graph that I made. Bam! Wow, would you look at that? Would you look at that? I'll hide this little guy here. Bam. So, so here is the blue line, all right, is a line. Notice I can actually accomplish lines in any quadrant with any slope. Well, I guess line in a quadrant doesn't technically make sense. But notice like here I can actually get any y-intercept and any slope that I want. All right. Right, so if I can do all sorts of crazy things, right? Good stuff, good stuff. So it turns out that I can represent this line a different way than perhaps we're used to. Let me grab a snapshot of this. And this is what normal form for the equation of a line is going to be. Normal form, normal form. All right, so if I happen to have the following sketch, all right, here's my little picture. Good stuff, good stuff. First of all, I just want to point out that this orange line, all right, is perpendicular to the line that I'm trying to describe. All right, and it passes through the origin. And there's a couple things we'll talk about here. We've got this angle from the positive x-axis. So if this was over here, I'd be talking about an obtuse angle. If this was down here, I'd talk about a wombo angle. I don't know. Obtuse. Still, it's just more obtuse than other ones. So this angle here is going to be one of my components, and it's going to be represented by the Greek letter phi. All right? It's just an angle. And the other thing that I'll use to describe my line will be the distance that the line is from the origin at its perpendicular. And that will be, I don't know what I was just going to say. I almost just said the human letter P, as if Greeks were not human. Oh my goodness, I think I'm some sort of ancient racist. Although there are do modern Greeks still use Greek alphabet? My ignorance is making me feel terrible. As if ancient Greek alphabet isn't as good as modern symbols. It's like, man, you guys are so in the past if you actually use those letters. Oh, I'm terribly sorry, guys. I've just revealed myself as some sort of racist, apparently.
There goes one viewer.
Yeah. I've just lost my one viewer. So it turns out this right here is the equation. I'm out of space here, guys. Meh. There we go. That's fine enough. I'll just rewrite that little piece here. All right. So here's normal form. It is x times the cosine of phi plus y times the sine of phi minus little p is equal to 0. Huh. Okay. And you don't have to write down this whole wordy description down there. But you could say that p is the length from the origin to the line. All right. Specifically, I guess it's the normal one. And phi is the angle between. Yeah, we're going to use this for a little while. It's going to be good. It's gonna be good. So it's interesting that you can define the location of a line from an entirely different perspective, right? Instead of slopes and y-intercepts or points and slopes, I'm describing it based off of a perpendicular perspective to it. All right, like the shortest distance to the line from the origin. Sort of thing like that. So yeah, so this is interesting stuff. So for our first example, implementing this, let's talk about, all right, let's pretend we're afraid of normal form, which we probably are, and let's pretend I want to get as far away from it as possible by rewriting an equation in standard form. Oh dear, what did I just do? There we go. So, write an equation of a line in standard form where p is equal to 6 and phi is equal to 150 degrees. 150 degrees. All right. So first of all, let's plug this into normal form just to see what this looks like. So this would be x times the cosine of 150 degrees plus y times the sine of 150 degrees. And let's see, if p is 6, then I'm going to have what here equals 0? Minus 6, all right? So it's always minus the p. That 6 looks like a G almost. There we go. And just graphically, so you understand what I'm referring to, I'm referring to a line, imagine a 150-degree angle, somewhere like this, all right, 6 units away. All right, so you can imagine that point, right? And now the line that I'm referring to would be the one that is perpendicular to that. Okay, so just so you understand what I'm representing with this equation. So if I want to write this in standard form, well, I can just actually evaluate some of these things and simplify. So let's figure out what is a cosine of 150 degrees. Well, reference angle, that's the same as the negative cos of 30 degrees, right? You guys are all good with your reference angles, I'm sure of it, right? Because the reference angle right there is 30. 30 degrees. Maybe, it could be. I was thinking that. Plus y times the sine of 150. Sine is positive in the second quadrant, so that's sine of 30 minus 6 equals 0. And negative cos of 30 is negative square root of 3 over 2 times x plus sine of 30 is 1/2 times, not sine, times y minus 6 equals 0. Now, you might recall back in the days of standard form that there was actually, we would typically have a, b, and c as integers. And we also had a greater than 0, which is just some constraints that they had. Now in this case, we won't be able to have a, b, and c as integers because I've got an irrational number there. But I can at least get rid of the fraction part. All right, how could I get rid of all of those 2's in the denominator? Multiplying by 2. And if I wanted the value of a to not be negative, I could multiply by negative 2. So I would end up with the 2's cancel out, the minus signs cancel out, to get the square root of 3 times x minus y plus 12 equals 0. And whatever, this is the closest I could get to standard form, where cap A is the square root of 3, cap B is equal to negative 1, cap C is equal to, I guess I'll call that negative 12 like I did earlier. All right, so just to point out, you can convert from normal to standard.
That's positive, all right.
Well, I'm just trying to get us into the habit of, I mean, I think I've seen it both ways. It's crazy. Isn't that a... Well, that's what I was saying. Standard form is so unstandard. But this is the standard form that I typically teach in lower math classes. And then this is the one that we happen to use for this text. So in order for the value of c to be the same between these two, I figured this would be a minus c away. So I would just have that be the opposite. And that's helpful for us in the sense that we have a negative p here as well. Because if I had that on the opposite side, then it would have been positive. But yeah. Isn't that a Sean Spencer quote? I've heard it both ways. I think if you search that on the internet, you'll know what's up. Psych. Yeah.
It's ending.
Yeah. So anyways, so here's our equation in standard form. Let me talk about this. If I want to change from standard form to normal form, this is a little bit crazier. To change from standard to normal. This is our technique that I will lay out for us. It's sad that it didn't fit all in one line. Alas, I'll live with it. Also, I didn't like this little square root from my Google Doc. I'll just patch in that corner there. No one can know. It's good enough. So the standard form of a linear equation, ax plus by plus c equals 0. Yeah, there's positive c, whatever. Can be changed to normal form by dividing each term. All right, this is the key. Divide each term by this guy. What? Don't write the whole thing, but at least write down the dividing each term by this. All right. So A and B are respectively from, you know, the values of standard right there. And it says the sign is chosen opposite the sign of C. I guess I might as well commit to this positive C thing, huh, don't I? Yeah. We'll call C positive 12 here. Fine. Fine. I know, I'm changing things.
I still need to write that down.
Yeah, I'm going to come back to it. I'll come back to it, because this will be important. Right. Oh, that was a squeaky shoe. Squeaky shoe. My shoes are falling apart. They're Skechers. It's the S. S is for squeaky. So, so divide everybody, each term, by the square root of a squared plus b squared. It's actually related to the distance, if you think about it. If you think about it. It's related to the distance. Distance. Right, because distance formula is the square root of x2 minus x1 all squared plus y2 minus y1 all squared. It's also related to the Pythagorean theorem, which you could see that this is related to. So yeah, so this is what that's pulling from. So let's do a couple of examples of this technique. And I think that's all we've got to do. Man, there's my cursor. I get lost sometimes on these bright days when there's snow on the ground. Exemple. So, write each equation in normal form, then find the length of the normal and the angle it makes with the positive x-axis. You can just summarize those directions, write each equation in normal form.
The length of the normal?
The length of the normal, that's the value p.
Oh.
All right, and the angle is the phi. Phi. So for this, what's the value of A, B, and C?
6, 8, 8.
Yep, 6, 8, and I'll just say C is positive because I don't actually need it for anything else. There's no blood type C positive, fortunately, so I won't mix it up with something like that. So let's see. So the thing I'm dividing by will be, if C is positive, I want to divide by the negative square root. Yeah. Of 6 squared plus 8 squared. So that's negative square root of 36 plus 64. Ooh. It's the negative square root of a hundo. Oh, what? No, they didn't. It's plain old negative 10. All right, so that's the first thing I have to do. And now what I'm going to do is just divide each side, which results in dividing each term, by this negative 10 character right here. So I'll have 6x divided by negative 10 plus 8y divided by negative 10 plus 3 divided by negative 10 equals 0, technically divided by negative 10, but it's always going to equal 0 all the time. So let's simplify these. So this simplifies to be negative 3/5 x plus, nope, minus 4/5 y minus 3/10 equals 0. So now this is technically in normal form. You might not spot it, but this part right here is equal to the cosine of phi times x, right? And this is equal to the sine of phi. And this is equal to the negative p. Well, because that was the setup from the equation. So if I want to figure out what phi and p are, I could just solve this. Cosine phi is equal to negative 3/5 if I solve this for phi. So let's see. Cosine phi is equal to negative 3/5, and sine of phi is equal to negative 4/5. So what I'm going to do, because if I just tried to solve one of those equations, I would have ended up with a 2-solution answer, but that's not what I'm interested in. But because I see both of them, all right, cosine is negative, sine is negative, I can actually narrow down what quadrant I'm in. What quadrant is both sine and cosine negative?
The third.
The third quadrant, they're both negative, right? So I know I'm in quadrant 3. So when I solve this, I'm actually just going to get the reference angle. Well, we'll cosine inverse both sides. Tell you what. Cos first. And if I want to plug that in a calculator, it's actually going to give me an angle here. And that's not what I want. And since I want the reference angle first, the reference angle for this is just going to be cos inverse of the positive 3/5. So that'll at least give me the one in the positive quadrant there.
Sorry, what's the purpose of the subscript R?
That was just my own notation for like reference angle for phi. I figured it was a good name for it. And let's see, so cos inverse of positive 3/5 is 53.1301 degrees, which of course you guys know from the hand trick. Of course not. I used a calculator for that, please. So if that's the reference angle, but I'm interested in this quadrant, what do I do? Add 180 to that. Right, so phi is just going to equal that plus 180, which is 233.1301 degrees. So there's phi. And what's the value of little old p?
So you don't have to find it for sine? too?
Well, they theoretically would equal the same thing. So let's see, what's p going to equal? 3/10. Or 0.0 or 0.3, sorry. Right, so here's normal form. Here's phi, and here's p. Now, oddly enough, what if I took this normal form and multiplied both sides by -1? Then I would have all positives. I would have had cosine equaling a positive and sine equaling a positive. And that would have been in this quadrant, and p would have been negative. So that's actually an interesting thing, is that there's 2 ways of writing an equation, well, as long as I'm restricting phi to between 0 and 360 degrees. But if I had phi landing in this quadrant, you could actually say at this angle in a negative direction. And that would have still landed me at the same spot to get my equation of the line. So I could have a positive value of p or a negative value of p, and my angle is just going to difference by 180 degrees. So it's just kind of a little bit weird, but I just wanted to point that out. That technically I could have multiplied both sides by -1 and had a legitimately equivalent in value answer for normal form. All right. That's also similar to point slope form. Technically had infinitely many equations that could represent the same line because there were infinitely many points on that line that I could have plugged in for that point. All right, last example. Last example, yeah. Not bad at all. Same direction, so you guys don't have to rewrite the directions if you don't want. So if I've got negative x plus 4y minus 6 equals 0. So first things first. Technically this isn't in proper standard form since the value of a is negative, but like I said, I've seen books call it all sorts of different things. A is negative 1, B is 4, C is negative 6. Or I'll just write negative, because that's all I'm using it for is its sign. So for my little square root friend, what do I want? The positive or the negative square root? Positive square root, right? Because it's the opposite of that. A squared, negative 1 all squared, plus 4 squared. Man. So that's the square root of 1 plus 16, or the square root of 17. So what I'm going to do is divide every term by the square root of 17. So I'll have negative x divided by the square root of 17 plus 4y divided by the square root of 17 minus 6 divided by the square root of 17 equals 0. And of course, any good mathematician, well, I wouldn't say that, I guess. There's been some recent discrepancies about leaving radicals in denominators, but I could rationalize those denominators multiplying top and bottom by root 17. So this would be negative root 17 over 17 times x plus 4 roots of 17 over 17 times y minus 6 roots of 17 divided by 17 equals 0. And this is technically normal form. Completely normal. So, that means that the following are true. That means cosine of phi is equal to what? Yep. And that means sine of phi is equal to 4 roots of 17 over 17. Right? So, in which quadrant is cosine negative and sine positive? Yeah, second quadrant, right? Negative, positive. So I'm in a second quadrant here. So I can solve this. What's up? Yeah. Miranda, do you have a comment, question? What's up? Okay, excellent. So let's see, cos inverse both sides. Well, that means phi's reference angle is going to be cos inverse of the positive of that. I'll figure out the signage later. Which is, technically it's an approximation here. 75.9638 degrees. And yeah, I rounded up to the 8 there. So if that's the reference angle, but I'm in quad 2, what do I do? Subtract it from 180, yeah. Yeah, reference angles, those are huge concepts for all of this stuff. Keeps coming back. So 180 minus that, I would get 104.0362 degrees as the value for phi. And the distance, the value of p, is the opposite of this. So that's 6 square roots of 17 divided by 17. Which if you wanted a decimal approximation, I believe that is about 1.46-ish. Let me see if I can do you one better on that. 1.4552, how about? So that means the line I'm talking about, go 104 degrees, then out 1.4 units. All right? we'd have that point there, and the line that is perpendicular to that through that point is the one I'm referring to and describing.
You can find it because it's always a 90-degree angle.
Yep, it's always perpendicular to the normal. So anyway, so there's that's the idea behind working with equations of lines in normal form. Thanks for watching, internet friends. Bye-bye.